Hi, everyone. My name is Jennifer Burt, and I'm a postdoc at JPL, where I focus on precision RV mass measurements of exoplanets. Today, and a couple of weeks from now, during the live version of the Sagan workshop, I'll be talking to you about strategies for mitigating stellar variability in RV data. Now, you might have already seen some version of this gorgeous new video that was released in celebration of NASA's Solar Dynamic Observatory's 10th birthday earlier this month. But even if so, it's amazing and definitely worth seeing again. Now, the full video is over an hour long, and it showcases years of observations of the sun, in which you can see everything from planet transits to eclipses to coronal mass ejections. But in addition to all of those discrete events, you can also see the variety of time-evolving phenomena that blanket the surface of the sun. Even in just a couple of weeks of observations shown here, it's very clear that our sun is not just a homogeneous ball of gas. It has structure on a variety of temporal and physical scales. And that fact should terrify, at least a little bit, any planet hunters in the room. Because as far as things go in the galaxy, our sun is actually considered to be pretty darn quiet. Now, trying to mitigate that variability, which is seen here in the recent release of solar RV data from HARPS North, where it completely overpowers the RV curve from the Earth, which is shown in blue, is a daunting task. And even though my talk is quite literally titled, How to Mitigate Stellar Variability, I want to be upfront with you about something from the get-go. The truth is, we don't entirely know how to do that yet. The last decade has seen a whole slew of new methods come onto the scene, and many of them have proven effective at measuring and characterizing and modeling out some portion of stellar variability. But as of yet, there's no reliable way to correct for all or even most of the variability that's exhibited by even the quietest of stars, such as the sun. It's an area of active research, and it's somewhere that we need many more clever and driven folks to get involved, hopefully including many of you in the future. But that said, let's look at what we do know at this point in time. So as Heather and Annalise have mentioned in their earlier talks, there are numerous types of stellar variability. For more detail, you should go and check out their presentations, as I'll provide only a quick overview here. But starting at the long period side of things, we have magnetic activity cycles that are driven by stellar dynamos. These cycles often last many years. For example, the sun's cycle is roughly 11 years, and they result in the star going through phases of high activity and low activity. Now, looking at this image on the right from the SOHO mission, you can see the strong magnetic fields that show up as bright spots in the sun's outer atmosphere, and those signify the years where there's high activity. And then the years where the sun appears much darker are the low activity years. These cycles often introduce RV amplitude variations at the level of anywhere from 1 to 20 meters per second. And so even though they are long, relatively broad cycles, they can have large impacts on your RV data. People have been tracking the number of sunspots on the sun for hundreds of years at this point. And you can see that although the exact amplitude and period of the magnetic cycle do change a bit from cycle to cycle, overall it's a pretty strongly recurring event. We have a decent sense of what it looks like in our own sun and in a number of other stars, as I'll show you later on. Next on the list are active regions on the sun's surface, things like star spots, faculae, and plages. These regions are areas of convection where significant magnetic fields are present, and they can induce RVs of up to tens of meters per second. In comparison to star spots or sunspots, which we've been tracking for centuries, the bright facula on the sun have been studied relatively little, but they dominate the surface of slowly rotating sun-like stars, and they can actually drive the RV variations of the sun. So they're an area of research that we're pushing on right now because we need to understand these better if we want to be able to get better RVs on sun-like stars. Oh, and there's a video that shows just a few days of time where you can see these kind of bright regions flickering across the surface of the sun. Taking another step down in time scale, granulation and supergranulation are manifestations of convection that occur over time scales of hours to days. And so you can see this kind of bubbling on a zoomed in portion of the sun's surface taken by the NSF's new DKIS telescope. Sun-like stars have a radiative core and a convective outer envelope. And within that envelope, hot bubbles of plasma, or the granules that you see here, rise to the surface. And so they have a blue shift because they're moving towards us. And then they cool off and sink back down in the intergranular lanes, or those dark outlines that you see between the granules. So because most of the surface area is taken up by the granules themselves as compared to the intergranular lanes, this results in a net blue shift towards us. And that can have a variability of up to a few meters per second and occurs on timescales of 20 minutes to a day or so. And then finally, the shortest type of variability are acoustic oscillations. These are caused by sound waves inside the sun that cause the visible solar disk to pulse in and out. That motion can be described as a superposition of literally millions of different oscillations, including the one shown here, kind of frozen in time, where the red spots are the areas pulsing outwards and the blue spots are the areas pulsing inwards on the star's surface. The sound waves, which are shown as the black lines in the cutaway part of the diagram, resonate through the star and are produced by hot gas that's churning in the convection zone, again, lying above the radiative zone and the sun's core. And so these pulsations occur on timescales of minutes, often 5 to 15 minutes for sun-like stars, and they have an amplitude of a few meters per second. So those different stellar phenomena, plus some others that I've skipped over in the interest of time, all help to produce the variability that's evident in this set of solar RVs, where you can see that even after all of the planetary signatures have been taken out of the data, because we know where the planets in our own solar system are, that we still have variations at the plus or minus 4 to 5 meter per second level, which again is huge compared to trying to find the signal of something like an Earth analog, which has an RV amplitude of 10 centimeters per second. But with just the RV measurements for a star, it's almost impossible to disentangle which bits of the star's motion are due to which type of variability versus the presence of planets, let alone to accurately characterize the different variability components so that you can model them out appropriately. So how do you actually detect and measure stellar variability? If we want to treat these different forms of variability as signals as opposed to just noise that we're trying to average over, then we need some way to detect and measure them, either within our RV data or from some other auxiliary data sets. Now, fortunately, the high resolution, high signal to noise spectra that are necessary to produce precision RV measurements also contain a plethora of additional information that we can use for exactly this purpose. So now we're going to look at some of the activity indicators that we pull out of our RV spectra. Possibly the best known activity indicator for RV surveys is the Mount Wilson S value, which is based upon the calcium-2 H and K absorption lines that lie down in the blue part of the spectrum. These lines reflect the star's chromospheric and photospheric activity levels, and when a star is more active or has more spots on its surface, then we expect to see the cores of these two lines show signs of emission. And so in this example on the right-hand side, you can see the very broad calcium H line on the top and K line on the bottom. For the inactive star that's plotted in blue, you can see that these form kind of a traditional absorption triangle. But then for the active star that's shown in red, you can see that the very core of each line starts to show signs of emission. So it peaks up above where the natural absorption profile would be. By measuring the level of flux within these line cores as compared to some nearby continuum regions over time, we can then measure the star's activity level and look for signs of periodic variations. And when you look at the results of long-term S-value surveys, periodic signals abound. So this figure from Baliunas et al. In 1995 shows the S-values for just a handful of the stars that were tracked in Mount Wilson, and you can see that periodic or quasi-periodic signals are evident in more than half of them. And so we use this to look for signs both of stellar rotation and of these much longer-term stellar magnetic cycles that are happening on timescales of years to decades. Now, related to the S value is the R'(HK) index, and this is based on those same calcium-2 H and K lines. But one of the tricks with the S value or the S index is that it has a dependence on the stellar type. So based on the temperature or color of the star, you actually get trends in the S values. And so you can't necessarily compare the base activity level of a star or of different stars across spectral types. The R'(HK) index, however, applies a correction that's based on the target star's effective temperature, and this allows you to then compare across spectral types and can be very useful for trying to figure out how active stars are with respect to one another. So it also subtracts off the photospheric flux that falls into the S index filter, which is not related to magnetic features. It's rotation independent, and it introduces this additional dependency on spectral type. Now, while the R'(HK) value is much better suited for activity studies, it is harder to determine because you need to provide some measurement or estimate of the star's photospheric flux, and that's a tricky thing to do. but it is possible to convert a measurement of the S value of a star to a corresponding R'HK value by estimating a conversion from the S index count rates to the physical flux based on the star spectral type or class. And so by plugging in a B minus V value for the star, you can actually translate from the flux in the H and K lines, which make up the S index, to this R'HK value, as was done in Isaacson and Fisher in 2010 and a number of other works. If we look further into the red part of the spectrum, there's another well-established activity indicator, which is the H alpha absorption line. Similar to the approach used for the calcium-2 lines, this indicator is based on the ratio of the flux in the core of the H alpha line and the flux in two nearby continuum regions. H alpha also tells you about the star's chromospheric activity levels because H alpha photons are emitted in regions where magnetic lines influence plages. This figure from Robertson et al. 2013 shows the H alpha absorption of Gliese 270 in states of high activity, shown in red, and low activity, shown in blue. And so when you have higher chromospheric emission, the red line, when the star is more active, you can see that once again it fills in the absorption line and increases the flux level there. By extracting this indicator from the time series, we can again look for evidence of sinusoidal variations that suggest the presence of star spots rotating on and off the star's face. And this is pretty clearly evident in this data for Gliese 270. H alpha can be especially useful for detecting periodic signals in cooler stars, both because the calcium H and K lines are often permanently in emission for those stars, and so they're not exhibiting temporal variations, and because for cool stars that are redder, there's often just not a lot of flux in the blue part of the spectrum. And so trying to extract calcium lines in early M stars down to mid and late M stars can be very challenging because the data just gets very scruffy due to the small number of photons coming out. And then even further into the red are the three lines that make up the calcium infrared triplet. And so this is considered by many to be one of the more promising activity indicators for the growing population of near-infrared precision RV spectrographs. Following a similar approach to the previous indicators, here we're measuring the flux in each of the line cores and then weighting it using nearby continuum bands. In this figure showing each of the three triplet lines, we're seeing observations of high activity in red, low activity in blue, and then kind of an average activity in black. And you can see that, again, the red line, the more active time sample, is showing signs of increased flux in the different activity indicators. Now, these lines all show a clear anti-correlation with the H alpha line that we just talked about, shown in the bottom plot here, which suggests that they're also sensitive to variations induced by spots, plages, and faculae. Now, in addition to looking at specific absorption lines, we can also consider the shape of all of the absorption features in a spectrum, because true Doppler shifts, those that are imparted by a planet, should preserve the shape of the star's absorption lines and should not produce any line asymmetries. A Doppler shift is just a lateral motion in wavelength. But line shifts that are due to stellar variability do change the shape of the line and will often introduce some sort of skew in the line shape. Now, the most common way to track line shape is using the line bisector, which traces the center of a line as a function of the depth below the continuum. So this is seen here as the horizontal lines that are measured at a given depth. And then you can see the V1, V2, and V3 positions that are marked, and that's the central position of the bisector. And you can also measure the full width half max of the line, which is depicted by the red arrow here. Now, the span of the bisector is the difference in the bisector position near the top of the line and the bottom of the line. That's measured in units of velocity, and it's usually designated as BIS in papers or when you see it on plots or periodograms. So if you look on the right side of the plot here, the bisectors have been extracted for two different phases of this potential planet's RV phase curve. And you can see that at the first phase, on the left, all of the bisectors on the bottom portion of this are on the right side of that dotted central line. Whereas on the left side, all of the bisectors at 180 degrees later in phase space are on the left side of the line. And so if you compare bisector measurements with the phase or the RV amplitude of a sine curve, and you see signs of significant correlation, which is what we see here for HD 166435, that should throw up a red flag. The signal is not due to the reflex motion of an orbiting planet. Rather, the spectrum is likely being affected by some type of stellar variability that's skewing the line shapes in addition to shifting them back and forth. And so in this case, it's stellar activity that's causing these movements, not a planet. The chromatic index is another way to look for signs of variability. So it was first shown by Zeichmeister et al. In 2013, and it quantifies variations in RV semi-amplitude as a function of wavelength by measuring the K, the semi-amplitude value of a given signal in each of the individual orders of an Echelle spectrograph. And then you fit a line to the resulting wavelength versus K data set. The slope of that line is this chromatic index or CRX value. So for a Keplerian signal, we would expect that the RV semi-amplitude would be the same across wavelengths, whereas variability from spots should exhibit larger RV shifts in the blue portion of the spectrum than in the red, because the spots are cooler than the photosphere and show less contrast at those longer wavelengths. So in this example, which uses data from the Carminus spectrograph, there's a pretty convincing sinusoidal signal present in the RV data for the young star YZ Canis Minoris. But the chromatic index and RV correlation demonstrates the dominating effect in the RV variations is wavelength dependent, which is consistent with the hypothesis that they're caused by co-rotating features such as active regions on the surface of the star. Now, one advantage of the chromatic index over chromospheric emission lines like calcium H and K or H alpha is that it comes with a directional sense, i.e. it can be positive or negative, which tells you something about the temperature contrast between the stellar features causing the line and the star surface. Data from outside the RV spectra can also be extremely helpful when trying to better understand and quantify a star's various variability timescales. One of the most common supplementary types of data is precision photometry of a star. And so here I'm showing this clip that was made using data from the K2 mission observing the Pleiades. Now, I think this is a great example because even for stars in the same cluster, if you extract their photometric signatures, you can see that there's a wide variety of timescales and levels of variation demonstrated by the different stars. And so while for some of the stars, like Maya, there's what looks like a very clear rotation signature of spots coming on and off the star, for many of the others, that evidence is a lot harder to interpret. It's a lot more challenging to say if there is a consistent periodicity evident in these signals that tells you something about the star's rotation. Beyond searching just for periodicity, light curves can also be broken down into three main components that describes the star's photometric behavior. There's the range, or RVAR, if we're using the terminology from Fabian Bastian's work on this in 2013 and 2014. And that tells you about the overall photometric variability amplitude. There's the flicker, which tells you about the photometric variations on a time scale of about 8 hours, which is often what we can see in a given night. And then there's the number of light curve zero crossings, which is a measure of the complexity of the light curve. This is somewhat similar to the number of Fourier components that are present in a light curve. Now, these parameters that were first described by Fabian can be used to help determine both the star's surface gravity, but also the likely activity level even before RV spectra have been obtained. So they can be helpful in deciding which stars to pursue. Okay, so that was a bit of a whirlwind tour through some of the most commonly used activity indicators. I wanted to make sure you had a little bit of background on what those indicators are and how we measure them and what they tell us about the star before jumping into all the ways that we try to use those indicators to now mitigate the effects of stellar variability on RV data. And again, just to reiterate what I said earlier, this part is all still a work in progress. Okay, so option one for mitigating stellar variability is kind of a cheat, if I'm honest. One of the easiest ways to mitigate stellar variability is to just not observe stars that exhibit a lot of stellar variability, because then you don't have to mitigate it. So there are a few different ways to do this if you're setting up a new survey. You can use the information on a given star's Mount Wilson ELSE value or equivalent activity indicator to predict its chromospheric activity even before you obtain RV data sets. So by combining a star's median S value with its B minus B color, you can then calculate its expected RV jitter based on the steps outlined in Isaacson and Fisher. This is exactly what was done for the Lick Carnegie exoplanet survey that ran for almost 2 decades on Keck. In general, as can be seen from the blue histogram above, they limited the survey to stars with expected stellar jitter below about the 5 meter per second level. The red histogram shows the actual median internal uncertainties for each star included in the survey, and as you can see, it ends up being pretty well matched to the expected jitter levels. For stars where you have photometry in hand and are deciding whether or not to pursue RV follow-up, you can use the FFPrime method that's described in the Agrane 2020 or 2012 paper to get an estimate of the star's RV jitter. In this case, the most light curve that was obtained for HD 189733 is shown in the top panel, and the observed and simulated RVs are compared in the bottom panel. And so the black dots with error bars show the SOFI data that was taken in Lanza 2011 after removing the best fitting photometric or planetary signal. And the gray line shows the RV curve that was simulated by applying the FFPrime method to the light curve. And you can see that that simulated RV curve actually does a pretty good job of tracking the real RV measurements that were taken. And so just from the light curve alone, you can get a pretty good sense of what the star might be doing in RV space. Now, another light curve to RV predictor is the star's flicker value, as I mentioned a couple slides earlier. This figure here from Bastien et al. 2014 shows the light curves of 12 Kepler stars and lists the RMS of the corresponding RV measurements. Now, the RV jitter is most sensitive to higher frequency photometric variability, especially when you're talking about low amplitude or not super variable stars. The light curves here, which are sorted by increasing RV RMS, show a general progression in their qualitative behavior from relatively low frequency variations in the top right to increasingly stochastic variability. The latter stars, despite appearing non-variable by traditional standards of photometric variability, where we look for kind of recurring sine curves that tell us, oh, we can see these discrete set of spots coming on and off the star, actually possess much more complex high frequency variability and in turn display the highest levels of RV jitter. Now, of course, the detailed behavior across figure 1 is not simply monotonic because some stars exhibit more photometric variations with both high and low frequency content, but nevertheless, it seems to be the high frequency photometric variability that most tightly corresponds to what the star is doing in terms of RV jitter. And so that's what we pay attention to. Now, once you've decided on which stars you do or don't want to observe, you then have to decide how to observe them. And good observing practices can actually help to mitigate stellar variability, especially when thinking about the shorter period signals. Now, the first and easiest to address are those stellar oscillations that are occurring in the 5 to 15 minute period range. And so if you make sure that your open shutter time on a given star covers at least that much clock time, meaning from when you start your first observation to when you finish your last observation, you've covered at least 5 to 15 minutes, then you should be averaging out most of the pulsations. And as an example, this is data taken for alpha Cen B, which is bright enough that the individual exposures are super short, and we can then bin them down into different total exposure times. And when the total exposure time is less than 15 minutes, you can see that the RV RMS is notably higher because the pulsation modes have not yet been averaged out. They're still independent signals that are impacting your data. But once you extend the exposure time out to 15 minutes or greater, then the RMS drops down considerably. Now, the exact averaging time necessary varies as a function of stellar parameters like effective temperature, luminosity, and surface gravity. So you can't just assume that each star should be observed for at least 5 minutes and call that good. But if you check out a paper that came out last year from Bill Chaplin et al., they've got a great, they've worked on how to characterize this for a variety of spectral types and stellar parameters, and they've even got a nifty little Python script which will tell you what observation time to aim for based on the stellar parameters that you input. Now, observing strategies can also help to mitigate the effects of granulation, which occurs on timescales of hours to day. The same concept can be used to average out the pulsation modes, can also be applied here. But in this case, you're trying to average out signals that last most of the night. Now, fortunately, there's no need to just sit on a single star for the whole evening, which would pretty much ruin any attempt at carrying out a successful RV survey where you want to look at more than one star. Instead, you can try to catch the star as it rises, when it's close to overhead, and once it's starting to set. And so by sampling a star multiple times a night with visits separated by 2 to 3 hours, you can go from the black lines on this plot, which show the effects of 1 measurement per night, to the dashed line on the plot in black, which shows 2 measurements per night spaced out by 5 hours, to the pink line, which shows 3 measurements a night spaced out by 2 hours. And so the more measurements you take per night, the better time sampling you have across that kind of 8-hour span, the better job you do of binning down the granulation and averaging it out, much like we did with the pulsations. And so while this is more observationally expensive and is going to mean you can observe fewer stars in a night, it might also mean that the stars you do observe, you're pushing down to a lower noise floor because you're addressing granulation in addition to the pulsation modes. Now, if you know something about the period of the planet you're trying to measure, you can also try to plan your observations to help amplify the Keplerian signal. In the case of Proxima B, there were multiple years of data that were taken before 2016, which is when the planet was published. Those are shown in the top left periodogram, and they suggested the presence of an 11.2-day signal. But despite the significance of the signal, you can see it peaking up above the lines showing where a significant signal needs to cross. Depending on the noise assumptions and exactly which subsets of data were considered, then you would get different resulting planet masses and periods. So in order to confirm the planet, the team undertook an intensive observing campaign in 2016, where they obtained one spectrum almost every night between January 19th and March 31st. And it was that set of concentrated data that provided the definitive detection. Now, at a semi-amplitude of 1.4 meters per second, Proxima B isn't an especially small signal, nor was the pre-2016 data set lacking in the number of total observations. They had a pretty hefty amount of data in hand already. So it appears instead that the uneven and sparse sampling combined with the longer-term variability of the star was the reason why the signal couldn't be unambiguously confirmed with the pre-2016 RVs. And so this approach argues that it can be helpful to take very intensive data sets over relatively short time spans when the activity of the star underneath you is more cohesive and can be modeled with, one or two signals, as opposed to trying to combine data from many, many years where the star can be evolving in a number of ways that makes it more challenging to then pull out the single signal of a planet. Another challenging case arises if you suspect the existence of a planet with a period close to the rotation period of the star. So the example shown here, there are two signed functions with periods of 3.24 and 3.35 days and similar RV amplitudes. And those were used to create an RV data set, which was then run through a periodogram analysis. The red periodogram curve is what comes out of a 10-day time series. And you can see that it shows hints of a signal at about 3.3 days in the middle of the two existing signals, but it doesn't have the baseline necessary to resolve that there are two different signals here. It thinks there's just one, and you get this kind of broad, washed out periodogram peak. It's only when a much longer observational baseline has been covered, in this case 300 days, shown in blue, you can actually resolve the two signals. And so if from something like a transit survey, you have suspicions about the existence of a planet, but it's close to what the rotation period of the star is, you likely need to not only have intensive observations, you need to have intensive observations over a long period of time. Now, even in cases where your observing strategy can't average out or mitigate stellar variability, you can still try to make sure that the data collected has all the right characteristics to help you try and model the variability after the fact. In particular, that means you want to aim for high resolution and high signal to noise observations. Now, these results from Davis et al. 2017 demonstrate how different combinations of resolution and signal to noise impact the number of principal components that can be recovered from the different simulated data sets, which have different spot and faculae coverage fractions. That's shown by the S equals 0.11 or 5% on the two left-hand sets of plots. In general, the more principal components that can be recovered, the darker part of the color plot that you are in, the greater the information content. So in an ideal world, you would want to be in the upper right-hand corner of each of these plots with spectral resolutions of 300,000 and signal noises of 1,500. Now, in general, it turns out that a resolution of 300K isn't readily available for any of the RV spectrographs that are on the market right now. And so most of us have to settle for actually being somewhere in the middle of these parameter spaces with resolutions of 100 to 150K and signal to noise values of somewhere between 100 to 300. That's kind of standard observing practice right now. But these kinds of very high signal to noise and very high resolution observations might become necessary if we want to truly understand the nuances of how stellar variability impacts line shapes in RVs going forward. So we might find ourselves eventually pushed into that right-hand corner, which would mean longer observing times, but much higher quality data. Okay, so let's say that you've collected the RV observations for your star of interest and you've done your best to follow these best observing practices. It's highly likely that even if you manage to take observations that average out the star's pulsation and granulation signals, there will be some sort of structure in the data left over from the stellar variability. So how do you deal with that? Well, one of the more straightforward approaches is to model the signals caused by stellar variability as additional Keplerians. This tactic is called PreWhitening, And it consists of looking at the periodogram of the RV data, fitting a sign function to the most prominent peak, modeling that peak out of the data, and then creating a new periodogram of the residuals. If any significant peaks remain, you identify the next most prominent peak, fit a sign curve for that, model both signals out of the data, and rinse and repeat until no significant signals are left. So the example shown here for Gliese 674, the most prominent peak in the initial periodogram shown in the top is due to a planetary signal. But the 3 additional signals that show up after you fit out that planet and look at the residuals periodogram are all due to the star's rotation or the harmonics thereof. And it's only after all 3 rotation periods have been modeled out as Keplerians that the residuals periodogram in the bottom goes from the initial black residuals periodogram, which is what's left over when you subtract out the planet, to the blue periodogram, which is what's left over after you subtract out the planet, the rotation over 2, and the rotation over 3 periods. And it's this blue residuals periodogram where we no longer have any significant features that we're concerned about. Now, this approach isn't perfect because activity-based signals decay over time and generally present as quasi-periodic, but if you only have RV data to work with, it's a solid first pass at trying to account for the effects that variability can have on the data. For cases where you have activity indicators along with velocities, which is what we generally strive for, we can start to get a little more creative. Now, one approach is to look at a time series of the indicator, in this case, calcium to H and K lines of the sun, and identify any prominent periods that appear in the calcium data. So this is the graph in the top left where we can see hints of a nice sinusoidal feature coming through on a long term, so probably a magnetic activity cycle. Once you identify the period of the variability in the calcium data, you can then use the derived period from that as the basis for a sinusoidal function that you fit to the RV. So this is shown in the bottom plot on the left. And so in this case, we have applied a sinusoidal fit where the period is locked to the period from the calcium data, but we've allowed things like the amplitude and the exact orbital parameters to float. That model is then subtracted from the original RV data set, and the residual RV shown on the right have been cleaned of sorts of the activity signal, and hopefully any true RV signals would be more apparent. A related approach is to compare the calcium and RV data sets by plotting them against one another as a scatter plot. And if a strong correlation is evident, then you can perform a linear fit between the two. Each RV point can then be corrected based on its corresponding calcium value, which removes the variability-based linear trend. Now, in both cases, the focus is on using information from the activity indicators that you've extracted from the spectra to then better understand the underlying stellar variability that's affecting your RV measurements and modeling or subtracting it out of the RV data as you start looking for planetary signals. Another approach, which works best for exceedingly short period planets, is the floating chunk method. In this case, observations taken over the course of a single night sweep out a non-trivial portion of the planet's orbital phase because the period is less than a day. So a given night's observations therefore appear as short segments of the Keplerian sign function. As you can see here in the plot, the full model is shown in red, and then each individual night's observations form one little chunk of the planet's actual RV sign curve. Now, the velocity segment on a given night has some offset that's due to stellar activity or additional long period planets or other things, as you can see here, based on how they're all offset from the red curve. But by including an additional nightly offset term in your fit for each night's worth of data, you can line up the segments and recover the planet's orbit. A nice example of this is seen here for the results of the ultra short period planet K2131b from Dye et al. In 2017. The circles are PFS data and the triangles are data from HARPS North, and the data is color coded where each color shows the data from a single night. And you can see how a single color, like the red triangles that show up on the left side of the plot, span a significant portion of the orbital phase, and this is what allows us to then fit for a comprehensive offset between all of the different nights of data. One of the most prolific planet detection methodologies of the past decade is the moving average approach, which applies a model built around the understanding that RV data contains a variety of signals, just like we've been talking about so far. These models include Keplerian signals to account for exoplanets, white noise signals to account for photon statistics, red or correlated noise to account for stellar variability, and then the option to fit for linear correlations between the RV data and available spectroscopic indices. The results, as you can see in this Bayes factor periodogram, is a comprehensive analysis that compares the 3 different noise models across the top columns, white noise in the left, moving average in the middle, and autoregressive on the right, and then applies them to the combined RV data set on the top, the individual instrument data sets in the next 2 columns, and then activity indicators like the S index and H alpha data, along with a window function of the RVs and the signal to noise of the data. So we're really piling in all of the different activity indicators and everything we know about the RVs to get a kind of overall picture of what's happening in this star. Now, if we zoom in on the RV data, on just the RV data, and compare the white noise and moving average cases here, you can see that in the white noise panel, there's a strong but somewhat broad peak at roughly 30 days. That's highlighted by the gold line coming down. And then there's another strong but scruffy looking peak, again a little bit broad, at roughly half of that period. And these are characteristics that are reminiscent of signals caused by stellar activity. This is the rotation period, we think, and then the p/2 harmonic, so half of the rotation period. This is all in addition to the much stronger and narrower peak at 12 days, shown in red, that we think is due to a planet. Now, if we look at the S-index data from one of the telescopes involved, you can see that that same 30-day peak shows up in the S-index value based on those calcium lines we discussed earlier. But there's not a corresponding signal in the activity indicators at the red line that shows the 12-day period that we think to be a planet. And so this confirms suspicions that the 30-day peak is due to activity and not another planet. Now, the benefit of the moving average model is quite apparent, as you can see in the right-hand panels of the top plot. The red noise model recognizes and accounts for the periodicity in the S-index data, and it removes that corresponding periodicity from the RVs, which also removes the p/2 harmonic. So on the right-hand plots, the planetary signal at 12 days is still very prominent, but the 30-day peak and its corresponding 15-day harmonic both have been removed. We're then left with a much cleaner period, or a much cleaner periodogram, in which the 12-day signal stands out, and that is indeed a new planet that we're writing up right now. So this works super well. And now finally, what is probably the most popular approach to mitigating stellar variability in RV data right now, Gaussian processes. Now, I'm not going to delve too deeply into the specifics here because Vinesh is contributing a whole talk solely focused on Gaussian processes, which you should definitely go watch if you haven't already. But I'll cover some of the basics. Gaussian processes work under the premise that variability signals are quasi-periodic with a handful of key parameters that help define their behavior, which are called hyperparameters. Users specify priors on the hyperparameters using information about the star's rotation period and how long spots last on the star, things that are often gleaned from other data sources like light curves or spectroscopic indices. The Gaussian process is then trained on a data set that contains information about stellar activity, be it photometry, S-index values, H-alpha values, etc. And it attempts to model what the star is doing alongside the planetary fit, which can allow for very reasonable RV fits to come out of data that's very impacted by stellar variability. In this top example, you can see that the expected semi-amplitude of the planet, which eventually gets modeled with the gold line here, is something like 5 to 8 meters per second. But in the very first few RVs that were taken on the left side of the plot, you can see that the RVs are spanning something like plus or minus 20 meters per second. So this was a pretty clear indication that the star itself was quite active and impacting what sorts of RV measurements we got. And so the way this was handled was that in the right-hand side of the plot, where there's this much denser sampling of radial velocity observations, those were actually overlapped with a ground-based photometry campaign, so that we had simultaneous radial velocity observations and stellar photometry, and then the stellar photometry was used to help train the GP, which is the blue line you see here, and produce this combined fit to the data, which does a much nicer job of being able to handle the fact that the star is active and doing a lot of its own motions behind the signal imparted by the planet. Another great example of this is Raphael Haywood's work on Corot 7 from 2014. So Corot 7 is a relatively small planet, 1.5 Earth radii, orbiting a pretty active star. And analyses of multiple sets of photometry from the Corot spacecraft revealed that the star's active regions on the surface were indeed evolving over time and changing underneath any signal that might be imparted by the planet. So in this case, the GP model was used to try and handle these RV velocities that you can see in the top panel of the left side plot, which have quite a lot of variability to them, a lot of up and down motion, again, at the plus or minus 20 meter per second level. And so a GP was trained to include factors for stellar rotation, which is the orange line in the second panel, stellar convection, which is the purple line, and then an additional term for other stellar variability shown in blue. And so the model then takes into account these three stellar terms, all shown in the second panel. Planet B, shown in the third panel, and planet C, shown in the fourth panel. And when you place all of those together into one final model, it produces the red line with the shaded uncertainty regions shown in the fifth panel. And you can see, much like the case on the previous slide, that this does a pretty solid job of being able to track the variations induced by the star and produce a fit that goes through the majority of the RV points. And indeed, when you look at the residuals in the final panel of the plot, you can see that there's not much structure or much correlated signal left in there, which suggests that we've properly modeled out the majority of what both the star and the planets are doing. And then the resulting planet fits shown on the right for planets B and C look great. So we have clearly done a nice job of taking out most of the correlated noise, but without eating any of the signal that's imparted by these two planets. But even in cases of copious high signal to noise data to train your Gaussian process on, you still need to be careful. So recent work by Molly Kucharik looked at 70 years of solar irradiance models from the Empirical Irradiance Reconstruction Project, or EMPIRE. And what she did was use a GP that she trained on each year of the solar photometry, and then let it try and figure out what was going on in the sun. What is the rotation period of the sun based in that year's data, and what is the evolution timescale for the spots that we see coming on and off. And so in the top figure here, you can see the hyperparameter that's fit to the amplitude of the stellar signal. And this we can see a nice job of tracking that 11-year trend that is the solar magnetic cycle we discussed earlier in the talk. And then in the third panel, we're plotting the recurrence timescale, or the hyperparameter that corresponds to the rotation period of the sun. And the first set of results I want to focus on are the black violin plots that are kind of plotted in the background of this. And these were the results from when she just applied a GP to the solar data and let it do its best guess at fitting what the rotation period of the sun was. And you can see that in the majority of these cases, the thickest part of the violin plot, the part where we think the answer is most likely to be accurate, does not overlap with the shaded bar. And that shaded bar is the actual rotation period of the sun. So what this is saying is that when left to its own devices, the GP does not necessarily get the solar rotation period right the majority of the time. But if you add an additional prior to the analysis, if you add a requirement that the spot evolution time scale, which is this what's shown in the second panel here, is longer than the rotation time scale, that is, the same spots last long enough that they come around multiple times around the sun so that we see them coming around through multiple rotation cycles, then instead of the black violin plots, you get the blue plots instead. And so these blue spots are actually doing a much better job of measuring the rotation period of the sun. You can see that in the majority of years, the blue plots in the third panel fall within that gray bar that is the right answer for the stellar rotation period. And so I find that this serves as a very clear reminder that we must always try to apply all of our knowledge about a given data set to the analysis, instead of just trusting exciting new methodology to handle the nuances for us. In this case, just applying the GP was not actually sufficient to get a handle on the rotation period of the sun, and it would have caused problems if we were applying this to some sort of planetary fit. It's only when we apply the additional knowledge that the spots last longer than the rotation period, which is something that's backed up by studies of many sun-like Kepler stars, we do see that spot evolution timescales are much longer than rotation periods for these kinds of stars, that we can actually fold that into the analysis and extract the right answer. Okay. So in conclusion, a couple of the big points that I hope came across in this talk. The first is that stellar variability that appears in RV data comes from a variety of physical phenomena within the star that occur on a variety of timescales. And so we have different periodicities and different amplitudes all interacting with one another to cause what can often be some very complicated background variability in the star. The effects of some of these phenomena, things like pulsations and granulation, can often be mitigated via good observing practices, but other types of phenomena, the active regions and the magnetic cycles, generally need to be handled in the data analysis phase. Obtaining auxiliary measurements, be it spectroscopic activity indicators or photometry, is crucial for determining what the star's activity looks like. And that's what we use to help train things like the moving average approach or the GPs that are used to mitigate stellar variability. And speaking of which, there are a large variety of ways to address stellar variability in RV data, but the approaches that treat the variability like correlated signals, the moving average approach, or quasi-periodic signals like the Gaussian process tend to perform the best. And so, as I said in the beginning, this is all still a work in progress. And I think that trying to overcome the difficulties presented by stellar variability will be the biggest challenge of RV science in the 2020s. But we're learning now to focus on much more detailed characterizations of the stars themselves, trying to understand not only what the radial motion looks like, but also how they breathe and shift and evolve on timescales from minutes to months. And as long as that focus stays sharp, then we'll keep pushing our understanding of how and why these different spectral phenomena, stellar phenomena, spots, plages, granulation, magnetic cycles, all impact the shapes and positions of absorption lines the way they do. And the hope moving forward is that that understanding will enable us to truly model the star's variability and then remove it from the RV data, making it easier to identify and properly characterize the signals of smaller and smaller planets or longer and longer period planets as time goes on. So with that, I will say thank you so much for your attention, and I'm looking forward to some excellent discussion about these topics and others at the Sagan workshop in a couple of weeks. Thanks.